Alright, this video is for our worksheet 1 for geometry. Say at the top of your worksheet I did put some of the helpful equations just so that you could use them to do this worksheet. So our first one, we have a body falls from rest on Earth, and we want to find, first of all, its displacement at 3 seconds. So first thing we want to do is we want to actually write down the variables that we have for just that first problem. So initially, if it tells us it's falling from rest, our initial velocity is going to be 0 meters per second. Our acceleration, which is pulling it down to the ground, is going to be 9.8 meters per second squared. And in this case, we want to know how far it's traveled at 3 seconds, so our time is going to be 3 seconds. So overall, what we're trying to find then is its displacement, which that's what we use our delta x variable for. So if we look at those things that we wrote down, go up here and look at our helpful equations, and which one of these has those variables present. So hopefully this was sort of the equation that you were looking at, 1/2 at squared plus v initial t. So all we need to do now is plug in our variables and solve for the x just as written. So we're plugging in our 9.8. We wanted to know our time at 3 seconds. We have an initial velocity of 0 times 3, but anything 0 times 3 can essentially just get rid of it because it's going to be 0. So to solve for this then, what we're going to do is we're going to take our 4.9 times 9. So all I'm doing is moving the numbers outward so we can get our distance of 41.1 meters. For part B, the time for it to reach a speed of 25 meters per second. You can think of this as a final velocity. So what we want to do is we want to calculate how long it takes for it to go from an initial velocity of 0 to this final velocity of 25 meters per second. Again, our acceleration that we have for this problem is our 9.8 meters per second squared, so it's gravity. We want to solve for how long, the time-wise, is it going to take us to get there. So again, let's look up here at some of our helpful equations. Looking at the variables we've written down, which one would be the most useful equation to solve for part B? So let's see, our equation as written up above is the velocity final minus the velocity initial over time. We can rearrange our variables, so we would actually get time is equal to velocity final minus our initial over acceleration. Now it's just a matter of plugging in our numbers. So 25 minus 0 over 9.8. So our time, you're just going to take 25 and divide by 9.8. So we get a time of 2.6 seconds. For part C, we want to know how long, time-wise, required for it to fall 300 meters. So that 300 meters is our distance, so that's our delta x. We still use the same initial velocity as we were given at the beginning of the problem, so 0 meters per second. We still have our acceleration because we're falling down to the ground. And we want to solve again for our time. Cancel. I must be hitting it with my arm. Alright. So for this one again, if we go up and look at our helpful equations, there is one that has all of those variables in it and time as well. So this equation that we're going to use is the same one that we actually used for our very first problem, the 1/2 at squared plus v initial times t. So we're plugging in, we have our 300, we have our acceleration of 9.8, we don't know our time, so we can put t squared, and our initial velocity again is 0, so anything 0 times t is still going to come out to be 0. So we can essentially get rid of that part. So if we wanted to solve for t, we're going to divide by this 1/2 times 9.8. So we do the same thing on both sides. And I'm going to write it over here. So we get t squared is equal to, so we're taking 300 and dividing by 4.9. So our times squared comes out to be 61.22, a big long decimal point. To get rid of our squared, we need to take the square root of that number. So we come up with then a time of 7.8 seconds for our answer. For the very last part of this problem, we want to find the speed after falling 70 meters. So just like the previous problem, this 70 meters is our delta x. We still have our initial velocity of 0. Our acceleration is still there. We have 9.8 meters per second squared. But this time what we want to solve for is we want to know how fast is it going to travel at the end when it hits that 70 meter mark. So scroll up, looking at our helpful equations up here. So there is one equation up here that does not have time at all. That's the equation we want to use for this problem. So we want to use our velocity final squared minus velocity initial squared is equal to 2a times our delta x. So plugging in our numbers, we get v final squared minus 0 equals 2 times 9.8 times 70. So we can get rid of that 0 and just say that our v final squared is equal to our 9.8 times 2 times 70. So that number comes out to be 1,372. Just like the previous problem up here where we had to use the square root, we're going to do the same thing for this one and take the square root of that number. So our final velocity then comes out to be, oops, and I hit the squared button, 1,372, square root of it. There we go. So 37 meters per second for our final answer. So all you have to do tonight then is just work through this one problem, come in with any questions that you do have about it, and tomorrow in class we'll actually work through the rest of our problems. So we have 2, 3, and, oh, just 2 and 3. I thought I had one more. That's it. So just those two we'll work on in class tomorrow. All right. See you tomorrow.